I'm actually very fond of if and only if statements, primarily because it sounds really cool to say to begin with. Because the if and only if sounds kind of redundant. Why not just say if or only if? But also it's like they allow you to look at a problem in two different dimensions, and it just adds to the complexity. And like as a math geek, I love it. So I thought of one that I haven't been tested on ever by my professors, but I thought I'd sort of recreate this if and only if statement by myself. And that's they're related to the Cauchy Schwartz inequality and the triangle inequality. As you know, the Cauchy Schwartz inequality, or CS, is written as it was A dot B is less than or equal to A B. I should put these vector arrows here. And the triangle inequality, or TE, shall I say, is written as A plus B is less than or equal to the A plus, sorry, I mixed that up a little bit. A plus B. All right, and I'm gonna write this as an if and only if, like this, saying I can use the Cauchy Schwartz inequality to derive the triangle inequality, but I can also use the triangle inequality to derive the Cauchy Schwartz inequality. So let's go with the forward sort of proof, if you like, first of all. I'm going to go from CS to TE. So let's consider this part. I'm going to show that this side of the inequality is less than or equal to this side of the inequality first. This cannot be done without the Cauchy Schwartz formula. So A plus B, I'm going to square it first of all. And that, as you know from linear algebra, is equal to A plus B dotted with A plus B. The vector dot product itself is its norm squared. And using the distributive properties of the dot product, that is equal to A dot A plus A dot B plus B dot A plus B dot B. But like I said, a vector dot product itself is its norm squared. So that is A squared. A dot B and B dot A are the same thing. The dot product is commutative. So we can just say that's 2A dot B plus absolute value of B squared. Now using the Cauchy Schwartz inequality, this is less than or equal to AB. So I'll say this is strictly less than or equal to A squared plus 2, using this is less than or equal to this, 2A B plus B squared. So I didn't change the other two terms. They're the same. I just only considered the middle term. And now if you only consider this part, that is, this part is actually just A plus B squared, and it's less than or equal to something looks funny. Something actually looks funny. Must be squared. Is that right? No, yeah. Sorry, it looked really weird for a flash of a second. Yeah. So this is still equal to this A plus B squared here, I think. I got a bit ahead of myself. A plus B squared, and that is less than or equal to, this, yeah, this makes sense. This is less than or equal to this A plus B squared. And of course, you can remove the square and you get the triangle inequality. A plus B less than or equal to the norms. And we are done for the forward proof. Now let's do the backward proof. This was an accidental proof. I'm gonna write it down before I explain it. This brings back so many memories. I was doing this in my Fourier PDEs class, and we were asked to prove the triangle inequality, and I did something like this. Watch. I'm gonna use the triangle inequality to prove the Cauchy Schwartz. Just watch. Okay. So I'm gonna start at this. Just write down the formula. A plus B. Okay, and I'm gonna square both sides. So that is A plus. Actually, you know what? I'm just gonna square it like this, show it this. I'm gonna square both sides of the inequality like this, okay? So as we learned, A plus B squared here from our previous proof, A plus B squared here is just equal to A squared plus 2A dot B plus B squared. And that is less than or equal to, and then from here we saw that A plus B squared was just equal to this, right? So that's A squared plus 2 absolute value A, B plus B squared. And we can cancel these two because they're like the same thing. And you get 2A dot B is equal to 2 absolute value A, absolute value B, but you can get rid of the 2 and you get A dot B is less than or equal to absolute value A, absolute value B. And we are done. This is the backwards proof. I remember this was an accidental discovery for me. I remember I was writing this to prove the triangle inequality, and then the TA wrote, this isn't a proof. You can't start off with what you want to show and then simplify, which I didn't know was not allowed at the time, but it allowed me to do this video. So occasionally, I guess you can say good outcomes come out of bad choices. So when one door closes, another door opens, right? All right, so that's all I wanted to show for this video. Thank you guys very much for watching. I'd love to stay, but for now, I gotta jump. I'll see you guys on the other side of the bridge. Catch you next time.